So now we're on a cubic element, so we're going up one more order, one more higher order function here. So from second order to third order. So even more accuracy using higher order approximating function. So we're going to approximate our temperature distribution now with cubic elements. So we got one-dimensional cubic elements require 4 nodes to define the element. And so we're going to need 4 boundary conditions. But here we go. Element 1 is made up of nodes 1, 2, so I say element's made up of nodes 1, 2, 3, 4. And we got element 2 is made up of nodes 4, 5, 6, and 7. So they both share node 4 there. All right. So again, you can see how it's going to have this curve. It's going to be able to match this temperature curve a lot better than the linear elements and a little bit better than the quadratic elements. And they're going to be spaced equally, so L 1/3 the length between each one of the nodes. We had K we added last time, and now we got M is the new node that we're adding here. All right, so there's our approximating function. And we're going to put in our boundary conditions. All right, so we know the temperature at each node, I, J, K, and M. So we're going to solve for C1, 2, 3, and 4 using these boundary conditions. And that's our resulting equation with the given shape functions being da 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 da. All right, so these 4 right here. So the thing to note here, so this is shape function node I. Notice that we have J, X at node K, and X at M. We don't have it for I. So that's kind of the pattern here. We got J, I, K, and M, etc., etc. So again, it's the overall temperature in the element. Any location X, we can figure out what the temperature is in the element. So again, generalizing, we can look at our psi variable here. So psi, cubic function. There's all our shape functions and then the resulting matrix form of that. Again, we could do this for temperature, we could do this for displacement, and we could do this for velocity. All right, so again, our shape functions still give us the same properties. So we have shape function for node I is 1 at that I's location, and J at is 1, shape function for node J at the J location. All right, and if we go anywhere else, so shape function node I is 0 at J, K, and M. And skipping here, shape function node M is 0 at I, J, and K. And if we add up all the shape functions, they'll equal 1. All right, so all the same properties match out there. So let's look at this Lagrange interpolation functions. So even higher order approximating functions. So we looked at linear, we looked at quadratic, we looked at cubic. So if we want to go to even higher order functions, they can be much more cumbersome and difficult to obtain the shape functions. All right, but there's the Lagrange method that makes it a lot easier, saves us from solving for C1, 2, 3, 4, etc. by using simultaneous equations. Instead, we directly write shape functions by multiplying several linear functions. All right, so here's the general Lagrange polynomial formula as for creating our shape functions. So if we wanted to get a shape function, say at shape function node K, this is how we do it. So this symbol right here, psi, is a capital psi, is capital psi, is for basically it does the same thing as the summation, but it does it for multiplication. So it's going to multiply each one of these. So you can see what it looks like over here as we do it. So if we take x minus m, and so we're doing from m is 1, starts at 1, and goes to n, whatever n value is. So you can see it starts at 1, 2, etc., etc., till you get to n. We omit x minus k. We omit x minus k. So why do you think we omit x minus k? Well, if we put in x at x sub k, so because we're looking at the shape function node k, if we put in, if this becomes the value at xk, then you can see that how it would be 0, and it would take out the whole numerator. Same thing here in the denominator. We're going to do x sub k, or x at node k, minus the global location of node m, and we're going to omit the point here where it's going to be 0 again. All right. So hopefully it makes sense why they omit those two particular ones there. All right, so for an n minus 1 order polynomial, we get That's how we solve it. So for a third order polynomial, right, n is going to equal 4. For a fifth order polynomial, n equals 6. So we have to do, n has to be 1 greater than the polynomial we want to look at. All right, so if we want to do a first order, n would equal 2. Right. So let's do an example here. Use a Lagrange polynomial function to find the shape function for a cubic element. So we already have this, but so we can kind of go through this and then look back and see what we got. All right. So again, we're going to do 1 notch higher for n than what we're actually looking at. So we actually want a third order, so we need to find n. So working backwards, we find that n is equal to 4. And our k is going to be equal to 1, 2, 3, and 4. All right, so here we're going to plug them all in to our function here. So again, n is equal to 4. And we got m starts at 1. And we're going to build this guy up here. So for node I, which we said is going to be 1, right, k is equal to 1. We're going to skip 1. That's where now 1's not here. We skip that. We omit that here in the numerator. So we get 2, 3, and 4. And we skip 1 minus 1, because that would be 0. And we'll keep 2, 3, and 4. All right, and then if we replace the 1, 2, 3, and 4 with our x, j, I, j, k, and m, then we end up with our function over here. All right. So here we got just rearrange j, k, and m in the numerator. And looking at the bottom, we replace it with the lengths. All right, you can see how we can combine those, and this is our final version of the shape function in node I. All right. So you can see hopefully the same form there. And let's go look back here. You can see these as we get all these here, here. So if we go back to the shape function here, you can see hopefully it's the same idea, same function as what we just came up with using Lagrange formulation. So let's go back here. All right, so if k here for node k, we're looking at that's 2. So it's 2 here. So we go 1, skip 2, 3, 4. All right, and we got 2, 1. We're going to skip 2, 2. And we go 3, 4. And then we replace those with our letters and substitute in the lengths in the denominator. And we get our final form of the shape function node k. Do that for node m, which is for 3. And we can do those as well. All right, for node m. And we'll do j at 4, the final one here. So again, we got 4, so 1, 2, 3, skip 4. 1, 2, 3, skip 4. Substitute back in the letters. And substitute in the lengths of the denominator, and we come up with our final function here for node j. All right, that looks great. So again, the shape function properties are retained because we got the same ones as we had for the cubic. We did this before, but value of 1 at its corresponding node and a value of 0 at its adjacent node, and they all equal 1 if we sum them up. All right, so it maintains those properties. So where do these shape functions show up? What's the importance of these? We'll go into more stuff later, but one thing, my Cool Flames article, so I wrote an article on Cool Flames. Let me show you that. As a kind of one place that it shows up. So when you talk about modeling, you need to talk about what kind of functions you use. So here I have this is talking about the numerical method I used for this particular problem, and I show you down here what was done. Here was the geometry, and you see there's obviously where all those connecting points are nodes, and you have the elements that surround them. So there's 2D elements. We're going to get more of this in a bit. But basically the same principles as what we've been doing with one-dimensional stuff. But I was looking at how a particular reaction occurred in this domain. And so I had to tell the reader, if anybody wanted to reproduce this model, how I did it. And to see if what I did was legit. So the whole thing about publishing articles is that you get a lot of peers to look at your work to see if you did it well, that we can trust the results from it. And so again, this is the numerical method section. And right up here you can see solutions were used using some software. The pressure field was discretized using linear Lagrange shape functions. We just looked at linear Lagrange shape functions when we looked at linear elements, but they basically developed from Lagrange, right? shape functions. All other variables, so those not including pressure field, which is the fluid velocity, temperature, and concentrations, use quadratic Lagrange shape functions. All right. So basically, people can understand when I show the results and we look at contours and stuff, how accurate were my results? You know, did I have linear functions between these nodes? Did I have quadratic functions that helped identify where the gradients were at? And so that was the big thing. So pressure, the field was basically consistent throughout the whole domain. Where I needed quadratic elements is that I would have large changes in temperature along this wall, because this wall was the cool part of my reaction, and the hotter part was out here in the middle. So there's a lot of gradients, a large change, rapid change in temperature from the wall out slightly into the gas that was modeled in here. And same thing with the velocity. There was a lot of velocity changes that were happening. And there were also concentrations. So I was looking at species and different, how species would change from essentially propane, oxygen to other intermediate species. So again, all those things were changing. So those ones got the quadratic elements, the finer evaluation versus the linear elements. All right, so hopefully that gives you an idea about how we can use those and the value of them.